Okay, so I've just changed the first two starting numbers. Everything else is the same. So if you increase the price by $5, you lose two customers. So if you increase the price by $10, making it a $100 product, then you'll have 1,196 customers, right? Because you lose two customers for every $5 increment. So for part A, for my problem, the price of my product is $90 plus 5x. Okay, because x stands for the number of times we increase or decrease the price. If x is positive 1, then we increase it by $5. If x is negative 1, then we decrease the price by $5. So that's it. That's all we have to do for part A. The price, it starts at $90 depending on how many times we decide to increase the price. And then for part B, we start with 1,200 customers. So that's how many customers we have. That's an expression for how many customers we have, but it's now going to be minus 2x. And I'm using minus because we have to go the opposite direction of whatever x is up here. If you have positive 1 for x, then you should be losing two customers, right? So this stands for the number of customers we have, depending on the number of times we increase the price. Okay, and then revenue means how much money we bring in. And it's just the number of products sold, which we have an expression for it. It's 90 plus 5x. And then the cost, the cost per product, I shouldn't say cost, the price of the product, because we're talking about revenue. What price are we selling it? You know, if you have 1,000 tickets, you sell them for $10 each, then you get $10,000 in revenue, right? So it's like we have this many tickets times this price for each ticket in that analogy I just gave. Okay, so that's it. That's the revenue function. You can expand this if you want. You don't have to, but you can multiply those two binomials together. Oops. That's 108,000. And then we got 90 times negative 2x, that makes negative 80x, negative 180x. And then over here, 5 times 1,200. That's 6,000x. And then subtract 10x squared. So we got 10,000, 108,000, and then plus 5,800, sorry. 20x minus 10x squared. So there's an alternate version of the same revenue function. These are equivalent, they're just rewritten. So that's it for C. Okay, this will be easier for the next parts that are coming up. For D, they tell us the cost depends on the price. P is number of products, I'm sorry. The cost depends on the number of products we sell. So to find a cost function based on X, there it is in function notation, then all we need to do is replace P with the number of products we're going to sell. And that's something we already did up here, right? This is the expression for the number of customers we have. So the number of products we sell is right up here, 1,200 minus 2x. And then we're going to divide that by 4. And that's it. That's all we have to do for part D. That's the cost. And then for part E, we're just supposed to write the profit function. This is just as easy as it might seem. It's the revenue, which we did in part C. So take the revenue, subtract it by the cost, which we got in part D. So the revenue is right up here, 108,000. Plus 5,820x. And then what was it, minus 10x squared. So that's the revenue, and we need to subtract that by the cost. All right, and that's it for part E. And then so for part F, it says how fast is the company's profit increasing? So this part is the real calculus part. part F and part G are where we finally got into calculus land. Okay, the profit, if we plug in a number in here, that'll tell us what profit we're making when x equals 4. But we're not asked for what our profit is. We're asked for how fast is the profit changing. So I'm going to use the calculus abbreviation, calculus shorthand for the derivative. We want to know a rate of change. We want to know how fast the profit is changing. So I want to take a derivative of the profit function with respect to x. And if I take a derivative, this term turns into 0 because there's no rate of change for a constant. This term is 5,820 because the 1 comes down and the power gets reduced by 1. And then this term is minus 20x. And then this term, the last term over here, that can be a little tricky. Remember, that's a 1/2 power. So if I clean this up a little bit, this is the same thing as 1,000. Here, let's divide 4 into both those things in the top. 1,200 divided by 4. That's 300 minus 1/2 x. But a square root means a 1/2 power. So if I'm taking a derivative of this term, the 1/2 is going to come down and multiply. The inside stays the same. Then the power gets reduced by 1. So 1/2 minus 1 makes negative 1/2. But then I still need the chain rule. The derivative of the innermost function is going to be negative 1/2. Because the derivative of this is 0, the derivative of this is negative 1/2. Okay, so we got 5,820 minus 2x, and then this is plus. Now this is all to the negative 1/2 power, so we can make that be a positive power by putting it in the denominator. So 300 minus 1/2 x, and then this is negative 1/2 times negative 1/2. That made a positive 1/4. Okay, so there's our derivative. And so all you need to do now for part F is plug in 4 into your derivative, which I'll let you do, because yours is going to be different. But the rest of that's just plug and chug. You plug in 4 in for x, and then simplify with your calculator. And that's how fast the profit is increasing or decreasing, depending whether it's positive or negative. Okay. And then part G, what should the company use in order to maximize their profit? We're looking for a local max or a local min, which means we want to set that derivative that I just calculated equal to 0. So set your derivative in part F equal to 0, and any place where the derivative equals 0 or where the derivative fails to exist, that's a critical point. And critical points are all the potential maxes or mins. Okay. So if I set this, if I first analyze for where the derivative fails to exist, I could have a divide by 0 problem over here. Or I could have a square root of a negative problem too, but let's focus on the divide by 0 problem. If 300 minus 1/2 x equals 0, then I have a place where the derivative is undefined. That's a critical point. So I can add that 1/2 x to both sides, multiply both sides by 6, and we get x equals 600. And let's see if that actually makes practical sense before we keep analyzing it. If x equals 600, that means we've lost 600 times 2 is 1,200. So we've lost 1,200 customers. So we might as well not even analyze that. If x equals 600, then we have no customers. So therefore 0 revenue, right? So that's not one we even want to consider. That is a critical point. Didn't turn out to be a maximum. So to find potential maximums, we just got to solve this equation. Okay, and then to find the other critical points, to set it equal to 0 and solve, I started doing it algebraically. And I realized that the algebra is probably going to be too much for the students that we have in the class, just because our algebra background might not be as strong as what's required for this problem. What you'd want to do is multiply this denominator to everything, and then multiply everything by this denominator again, or you could just multiply by 4 times 300 minus 1/2 x. And then eventually what's going to happen is you're going to want to move all terms other than a radical to one side, square both sides, and then the algebra just gets ugly, but it's just a lot of expansion from there. But for this last part, I'm perfectly fine if students use a calculator to help them. So we set our derivative equal to 0. We found where the derivative fails to exist. That turned out to be no good. That didn't help us find a maximum. So we can now solve to find out where this equals 0. So you can just go into Desmos and plug the right side. And by the way, this is desmos.com/calculator. Okay, plug the right side of that statement, that equation, I use 0.5 instead of 1/2 x, but plug that into your calculator, and then what you're trying to find is where the derivative, where this derivative crosses the x-axis. Oh, for my problem, it doesn't look like it's going to cross. So that means there was only one critical point. Okay, but I made up the numbers for my problem. So let me change something here. Okay, so I've changed it a little bit. Your problem will cross the x-axis, okay? Money back guaranteed. And so those places where it crosses the x-axis, those are the potential critical points. Those are the critical points. Those are the potential maxes or mins. So look, it already crosses 600, which we knew it was going to. Which we already knew was a critical point. We didn't know necessarily it was going to cross there. But it also crosses at this other data point at 410. And so 410 is the value you want to test to see whether it's a max or a min. So it looks like x equals 410 would be my maximum. If you test it, I'm just going to go ahead and tell you, you're going to find out it's the local max for your particular problem. Okay, again, I made up these numbers off on the fly, so mine looks different than yours. But if you find out where it crosses the x-axis, I've already set it up so that's going to be the maximum. So to find out what price it should be, you found out what x needs to be. You found out the number of times you need to change it. So to figure out the price of the product, you just need to plug in your number for x back in here, and then you've got the maximum, the price that would maximize your revenue.